Hi, welcome to another chemistry video. Today we're going to talk about net ionic equations. We're going to represent changes in matter with balanced chemical equations or net ionic equations. This is going to keep track of physical state changes. It's also going to look at ions in a given chemical reaction. Additionally, you're also going to have to be able to read a chemical reaction, so with the actual names written out, and provide a balanced chemical equation with proper formulas. Chemical equations are a shorthand method used to illustrate what's actually happening during a chemical reaction. Steps to writing a chemical equation are first, writing down the equation in words. This is usually provided to you in an actual question or description of a situation. Fill in the correct formulas for all your substances, and then balance the equation with proper coefficients. Key thing here is making sure you have the correct formula for all your substances. If you don't start with the correct formulas, you'll never end up with the proper balanced equation. Balancing equations can be tricky. Practice really makes perfect, but a lot of it is trial and error. But here are some steps and tips that can help you out. Ensure the formula are correct for your reactants and products, because once again, you can make an equation not even possible to balance if you have the wrong formula. Balance each element in turn. So again, you want the same amount of atoms of each element on either side of your arrow. So the amount of atoms of each element on your product side equals your reactant side. So it's really a step-by-step trial and error type of situation. If an element appears in one compound on each side of the equation, try balancing it first because it makes it a little easier if it only appears once. If one element is a free element, you try balancing it last because it's easily manipulated in terms of its coefficients. And again, remember, balancing only changes the coefficient. So the whole number in front of your products and reactants, you cannot change the formulas, the subscripts of any of your products or reactants. You are changing the actual chemical compound that's in your balanced equation if you change the subscripts. So then you're no longer writing the correct equation for the situation you're describing. You can also add state symbols. By state symbols, I mean represent solid, liquid, gas, and aqueous. Again, that's represented with the parentheses around S, L, G, and AQ. These aren't required in chemical equations, but it can be useful in some cases, especially if you're tracking whether something will actually dissolve or not dissolve in a substance. So a quick recap on formula. If you feel like you need more of a brush up on this, it's in the first few chapters of your textbook, and there's also plenty of YouTube videos I can point you towards, or we can do a little practice in class too. But for ionic compounds, you have to crisscross your charges, so you need to remember what charges some of the ions have. There was a list in the summer assignment. You have to remember that free elements are typically monoatomic, but there are exceptions. There's 7 elements that exist diatomically, so whenever they're by themselves in an equation, they have to be written diatomically. For example, if a reaction produces hydrogen gas, you have to write it H2. But hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are your diatomic elements that you have to commit to memory. Prefixes in covalent compounds tell you how many atoms are in the formula, and you do not reduce covalent compound formulas. So ionic compounds you do, covalent compounds you don't. But if you look at triphosphorus pentoxide, tri meaning 3, pent meaning 5, so you have 3 phosphorus, 5 oxygen. Again, for a more in-depth review, you can go back to your summer assignment. A good portion was doing this, or I can direct you to some videos. I'm going to pause the video, but I would like you to write balanced chemical equations for the following written out equations, and then come back and check your work. So here we have a hydrogen as a free element, so that's H2. Remember that the 2 goes with the metal, so this is copper plus 2 oxide. This would make CuO as your formula, producing copper, and then water H2O. Carbon, oxygen is diatomic. Carbon, 1 carbon monoxide, so CO. Magnesium, so just Mg. Sulfuric acid, H2SO4. H2 for hydrogen gas, magnesium sulfate, and here are your balanced chemical equations. So we have H2 plus copper oxide, making copper plus water, 2 carbons plus O2 to make 2 carbon monoxides. Magnesium, H2SO4 is your formula for sulfuric acid. Mg has a plus 2 charge. Sulfate has a minus 2 charge. We crisscross and reduce to get magnesium sulfate plus hydrogen gas. So many chemical reactions are going to be carried out in the aqueous solution, so where compounds are dissolved in water. Water is a very convenient solvent. It's readily available, it's fairly cheap, and very many solids dissolve anything polar is going to dissolve in water. So there's a few different ways to represent aqueous solutions. So the first thing that we need to review a little bit from Regents chemistry is electrolytes, non-electrolytes, and weak electrolytes. Ionic solutions are typically identified by the fact that they conduct electricity. That's one of their main properties. If there's a lot of ion solutions, the solution is going to be a really good conductor. If a substance completely ionizes, so 100% turns into ions, completely dissolves, something like sodium chloride, it's considered a strong electrolyte. All soluble ionic compounds are classified as strong electrolytes. Weak electrolytes make very few ions in solutions and therefore conduct weakly. And non-electrolytes, like molecular compounds, have no ions in solution and therefore won't conduct any electricity. And they're, again, called non-electrolytes. Here's some example equations. So strong electrolytes, like I just said, completely dissociate into ions. So if you take an ionic compound solid, add it to water, it completely breaks down into its ion counterparts. In this situation, the negative part of a water molecule, so the partial negative, meaning the oxygen atom, which is more electronegative, is going to surround the cation, so strontium in this case. And the positive part of the water, the less electronegative hydrogen part, surrounds the anion. Both cations and anions are completely surrounded by water and are referred to as hydrated. We also have weak electrolytes, which are only going to partially dissolve into water, so they produce very few ions, and they make an equilibrium. So this means that it's both your reaction from left to right and right to left are occurring at the same time. So the reaction is occurring in both directions, both the forward and the backward. And again, that just means that some of the compound is existing still bonded together while some of it does ionize. Non-electrolytes won't ionize at all, so there's no ions present, something like a molecular compound. Net ionic equations are a way to actually simplify and look at some of these compounds. So chemical equations of ionic compounds can be simplified, which gives you your net ionic equation. For example, here we have a full chemical equation. We have silver nitrate, silver nitrate plus potassium bromide, making solid silver bromide, won't dissolve in water, and potassium nitrate, which is aqueous. We can write out each of these compounds in terms of its ions. So again, silver nitrate will fully dissolve into its ions. It's a strong electrolyte, so we can write it as Ag plus and NO3 minus. Potassium bromide also is a strong electrolyte and will exist completely as ions in its solution. So we can write that as K plus and Br minus, their corresponding ions. Silver bromide is a non-electrolyte. It does not dissolve in water, so it will remain a solid and precipitate out of solution, form a solid in our solution. Potassium nitrate is aqueous and will completely dissolve into its ions and remain ions in solution. Now, if you look on either side of our chemical equation, we have common factors. We have our potassium ion on either side of the arrow and our nitrate ion on either side of the arrow. The potassium and nitrate ions are in the aqueous state on both sides of our equation. They remain unchanged, so they haven't participated in the chemical reaction. So they're called spectator ions. Spectator ions can essentially be, you can think of it as being canceled out in the equation. They remain in solution. They're not participating in our actual chemical reaction. So we get a net ionic equation where these spectator ions are removed. So we have our silver ion, our bromine ion, forming silver bromide. And that would be our net ionic equation. That's it for today. Tomorrow we're going to go over, again, how to actually write these out and practice that skill. If you have any questions, bring them to class tomorrow. Otherwise, have a good evening.